Today's lesson is on writing net ionic equations from word equations. We're going to approach this by categorizing the reactions the way that you've done in the past. We've got decomposition, we've got synthesis, combustion, single and double displacement, and eventually we'll add redox, and we've also got our complexation reactions that we learned this year. In order to become an expert at writing products for reactions, practice is the only way to do it. There are lots of different reactions. You need to approach it with a problem-solving attitude rather than a memorizing attitude. There are things to look for and things to recognize, but there is a little bit of intuition that comes with writing reactions, and that intuition is going to be developed either naturally, some of you will just have it, be able to kind of visualize and see what's going to happen, or some of you will need to really work at it and practice lots and lots of reactions. And there are lots of practice problems available. The way that we're going to do this is by going through each of the families of reactions and identifying some of the key features to look for. And then we're going to do some practice exercises that are from your booklet. I've picked a variety from each of the categories to cover some of the examples and to help us to discuss some of the important points when creating the net ionic equations. The first type of reaction that we're going to look at is the decomposition reaction. So as you know, this is a reaction where you have a molecule breaking down into smaller pieces. So you might have a compound, for example, breaking down into its elements. Okay, these reactions are often obvious by the wording where they've been heated. Okay, you've got one reactant and it's being heated. That's often going to signify to you that a decomposition reaction is happening, and how the compounds break down is based on what their components are. So if something's a simple ionic compound, it'll usually break down into its elements. What you want to be aware of here is making sure that the charges are appropriate for your ionic compounds when you're writing them, and you'll want to make sure that you're following Hofbrinkel for any gases that might be produced. Now sometimes compounds will break down into other compounds, and I've fixed the one in your notes and I've also added a couple on here. So if you've got ammonium nitrate, it'll decompose into oxides, N2O and H2O. And this is a good example because, this is very specific, and so you could memorize this if you wanted to, but you could also, and it would be acceptable for you to, in this case, to try to write products that were oxides. Often if you're stuck, if you make oxides of the elements in the reactants, then you're going to be on the right track. Okay, so these two are a little bit more predictable. I'll show you. They're also making oxides, but this one, you're going to make a nitrogen oxide and you're going to make a hydrogen oxide. So a nitrogen oxide, one example of that is N2O, and a hydrogen oxide is water. Carbonates, when they're heated strongly, will decompose and produce carbon dioxide and the oxide of the metal. Okay, so in this case I made the calcium oxide properly using charges, and then I knew that carbon dioxide was being produced. When you've got a sulfate and it's strongly heated, you'll produce the gas sulfur trioxide. Okay, and then you get the magnesium oxide. Okay, now combustion reactions are a bit different. They're also decomposition reactions because you're reacting with air or reacting with oxygen to produce oxides, okay, which is a bit different than these ones. These ones are just straight heating to decompose. So this is like chalk being heated up and decomposing. So the classic combustion reaction that you know of is carbon-containing compounds reacting with oxygen to produce carbon dioxide and water. You can also have sulfur-containing compounds that will produce sulfur dioxide and water. Okay, so a few things to look for here. You want to look for combustion reactions. Those ones are easy to identify. You want to look for gas production. Okay, so carbon dioxide, ammonium, okay, sulfur dioxide. If you've got a chlorate that's being strongly heated, you'll get a chloride compound and oxygen. Okay, so these are some highlighting some examples to look for. Synthesis reactions are the opposite. They're combining smaller molecules to make a product. And there's lots of different combinations. So you might take a metal with oxygen, okay, to make the oxide. So in this example, you've got iron plus oxygen making rust. You could take a metal and a nonmetal just to make a binary compound. Okay, so sodium plus chlorine producing sodium chloride. Okay, so these ones are both straight formation of ionic compounds, and that's something that's really important when you're writing reactions, is to write the formulas of your ionic compounds very carefully. Now, these next two are specific synthesis reactions that you need to be able to recognize. If you have a non-metallic oxide, so a non-metal with oxygen, and you react it with water, you will produce an acid. Okay, so something like SO3, which is a non-metallic oxide, reacted with water makes an acid. On the other hand, the metallic oxide, so a metal with oxygen, reacts with water to produce a base. Okay, so these are opposites. The non-metallic produces acids. The metallic oxide produces bases. Now the bases are pretty straightforward to form because you're simply taking the metal and combining it with hydroxide, okay, in the proper ratio, and then balancing the equation. The non-metallic oxides, you'll see sometimes they're a little bit trickier. Okay, you're going to be needing to create the appropriate polyatomic ion that's going to be used to make your acid, and that's not always easy. When we study oxidation reduction, we'll come back to this for a little trick that we can add. It's about the oxidation numbers. Okay, but you'll be able to see that trial and error is a possibility, okay, if you are comfortable with your polyatomic ions. Now, another kind of synthesis reaction that you can do is if you've got a metallic oxide and then you add some kind of gas to it, like CO2 or SO3, you can produce a salt. And I kind of think of these as sort of upgrading from an oxide to something with a polyatomic ion. And I think of this oxygen as combining or upgrading the gas that I'm using. So the SO3 here, when it's reacting with an oxygen, I'm gaining another oxygen, so that's giving me sulfate. CO2 is being upgraded essentially to carbonate here. And then I can produce the proper formulas for the ionic compounds. Okay, so here's a few little reminders. So always looking to use Hofbrinkel. That's important for all reactions. Okay, if you've got reacting with CO2, it'll upgrade to a carbonate. H2O, it'll upgrade to a sulfate. When you add H2O, and these are all two metallic oxides, it's either going to be an acid or a base, okay, depending on whether it's a non-metal oxide or a metallic oxide. And then also to always remember to use your charges when writing formulas. Single displacement reactions are examples of what are called redox reactions, where we involve an electron transfer. There's a whole section dedicated to redox reactions that we're going to study later, but we can manage at this time some of the basic redox reactions, which are single displacement reactions. So as you know, the general format for this kind of reaction is A plus BC going to AC plus B. So we can either have a metal displacing another metal, or we can have a non-metal displacing another non-metal here. This is the activity series of metals, and it basically puts in order the metals from the most reactive to the least reactive. So these metals at the top are more likely to lose electrons than the ones at the bottom. And what you'll see is that there's different sections here. So anything in this from sodium to lithium, these will react with water quite vigorously. This section here will react with steam, but you're not going to see that covered very commonly. Okay. Anything above the hydrogen here, these ones will react with acids to produce hydrogen. Okay. And then other than that, this list can be used to compare the reactivities of one metal to another. So for example, if I look at something like a piece of zinc reacting with a solution of copper sulfate, I can use the activity series to decide if this reaction is going to occur. Zinc is higher up on the activity series than copper. So that means that zinc is going to be able to displace copper. If it was the other way around, no reaction would occur. So I'm going to end up here with zinc sulfate and copper. Okay, so for example, if I did magnesium plus sodium chloride, okay, magnesium is lower than sodium, so no reaction would occur. One of the great things about the reaction section in the AP exam is that all the reactions that you're given will occur. So although it's important to recognize the activity series at this stage, the reality is the reactions are never going to end up being no reaction. So if you understand and are able to predict that when you've got a metal reacting with an ionic compound, you're going to have single displacement, that'll be good enough. The activity series for halogens. Okay. Halogens, much like metals, can displace one another. Fluorine is most likely to displace, okay, versus iodine, and these just fall in order the way that they're on the periodic table. So for example, if I've got fluorine reacting with sodium chloride, because fluorine is higher up on the activity series, it's going to be able to displace the chlorine here. So I will get sodium fluoride and chlorine gas. And I recognize that that's unbalanced, but we'll worry about that later. Okay, so the different kinds of single displacement reactions, you can have a metal replacing a metal. Okay, so in this case, the aluminum is going to displace the nickel. You can have a non-metal displacing a non-metal. So in this case, the chlorine is displacing the bromine. Now we can also displace hydrogen. Okay, metals can displace hydrogen. As you saw with the activity series, some metals will react with water and some metals will react with acids. When they react with acids or water, what they're actually displacing is hydrogen. Okay, so actually just picked up on an error here. So this should actually be H2. And this should be 2HCl. Okay, so when you've got magnesium reacting with hydrogen, if you look at the activity series, it does in fact react. Okay, and what's going to happen is the magnesium is going to displace the hydrogen. So the magnesium will combine with the chlorine in its normal formula, MgCl2, and what's being displaced here is H. And H gets displaced not as H+, but as hydrogen gas. Okay, this is a classic reaction you do in grade 9 and 10 science for the hydrogen test. Okay, it produces a good amount of hydrogen that you can test for. Okay, when you've got a metal with water and it reacts, so something like sodium plus water, and you've seen this in the past, I know. Again, you're going to displace hydrogen. What you want to do is think of water in this reaction as HOH. That'll help you to see what the products are. The sodium is going to displace the hydrogen as H2, and then the sodium is going to combine with the hydroxide. Okay, so your products here are sodium hydroxide and hydrogen gas. Okay, so these are the different examples. So these are just a few little tips here for when you're studying single displacement reactions. Okay. Complexation reactions we've spent a fair bit of time on. Okay. The key with these ones is to actually recognize them by the terms and the reactants and products that are involved. Okay, so as you know, you need a transition metal and you need one of the ligands. Okay, and these are often going to be concentrated or in excess. Okay, so for example, concentrated ammonia solution, so it's NH3, is added to an excess of silver nitrate. So we removed the spectators here, so you get Ag plus the ammonia. And as you know, the number of ligands is equal to double the charge. So in this case, we've got 2 ligands and the overall charge is +1. Double displacement reactions, there's a few different types. We've got ones where we can form precipitates, we've got ones where we form gases, and then we've got some acid-base reactions. Okay, so first of all, you need to know quite a few things. You need to know your solubility rules and be comfortable using them and applying them to be able to identify when something's going to be a precipitate. So if you perform a double displacement, so calcium sulfate plus sodium hydroxide, they're pretty standard, these ones. You've got 2 ionic compounds. And if you really don't know anything else that could occur, hey, try a double displacement and then use the solubility rules. So in this case, calcium hydroxide is being produced and sodium sulfate is being produced, okay, and calcium hydroxide has pretty low solubility. Okay. So that could be considered a solid. Okay, this isn't an ideal example. Okay, another scenario is when you've got a gas produced. So if you've got, and this is often an example of an acid-base reaction. So say I've got hydrochloric acid with sodium carbonate. Okay, when I do a double displacement reaction on this one, I get H2CO3 and NaCl. Now, what it's important to recognize is that if at any point you see H2CO3 being produced in a reaction, you need to recognize that as actually further decomposing into H2O and CO2. Okay, so this is why carbonates and acid produce carbon dioxide. Okay, because this H2CO3 decomposes into H2O and CO2. Another thing to look for is ammonium hydroxide. If when you do a double displacement reaction, if you get ammonium hydroxide, you need to recognize that as decomposing into NH3 and H2O. A couple of other gases, H2S, okay, it smells like rotten eggs. This particular gas is produced if you've got a sulfide and an acid. Okay. If you've got a sulfite and an acid, okay, so sulfite is SO3. Okay, so if you have something like potassium sulfite plus hydrochloric acid, you're going to produce SO2. Okay, typical acid-base reactions, if you've got a strong acid and a strong base, you're always going to get water and the salt. The other acid-base reactions that you need to look for are the proton transfer ones. Okay, so a few key things, and sometimes the double displacement reactions are actually on the top of more difficult, okay, in terms of transferring into an ionic reaction. What you need to do is look for soluble salts, strong acids, and bases. These are the only ones that are written as ions. You need to keep your eye out for these gases being produced. You almost want to expect them to be produced and look for them. Okay, and then the other little tidbit is that anytime a strong acid is listed as concentrated, you need to treat it as being molecular. So something like H2SO4, if it's really concentrated, there's virtually no water, so there's nothing for it to dissociate into. There's nothing for it to break up into its ions, so therefore it's considered molecular. So the formula that you would use is simply its regular formula rather than its ionized version. And as I've said a couple of times, we're going to be looking at redox reactions later on. Okay, so let's do a couple of examples here. In the decomposition category, we've got ammonium carbonate is heated. Okay, and as I said when we were doing our discussion earlier, okay, the words is heated, is strongly heated, those are key words in terms of decomposition. And if you look at decomposition, there's a couple of things here. Okay, oftentimes we'll be making our oxides, right? So if we look at the elements that we have here, okay, we've got ammonia, okay, we've got nitrogen, we've got carbon, and we've got hydrogen. And so this is going to eventually break up into smaller pieces. Okay? NH4 will often produce NH3, and CO3 will often produce CO2. Okay? So I would suspect that you're going to produce NH3, H2O, and CO2. And then you're going to look at whether or not this could be balanced, and it can be. Okay, you've got 2 NH3, and that balances the reaction. Now, a few things in terms of this being a net ionic reaction. There's this solids, okay, and then these are going to be all gases because this is being heated. Okay, so there's nothing to ionize in this case. Next one here, combination synthesis. Barium oxide is being added to distilled water. Okay, so you've got BaO plus H2O. Now, what you have here is a metallic oxide plus water. And when you've got a metallic oxide plus water, you're going to produce a base. So the base that's going to be produced here is barium hydroxide, so BaOH2. But because that's an ionic compound and it's a strong base, it's going to break up into its ions. Okay, so this is the net ionic equation. Calcium oxide is heated in the presence of sulfur trioxide. Okay, so I've got SO3 and metallic oxide. So this I think of as essentially upgrading the SO3 to a sulfate, and this is going to make calcium sulfate. Okay, calcium has a 2 plus charge, sulfate has a 2 minus charge. Now there's no indication of any water, so I don't need to consider the solubility and break this apart. Calcium metal is strongly heated in the presence of nitrogen gas. I need to remember that nitrogen is part of Hofrinkel. Strongly heated, I've got 2 elements here. So this is going to produce an ionic compound. Okay, by balancing the charges, I get Ca3N2, and so I'm going to balance this by putting a 3 here. Again, there's no indication of this being in solution, so it's going to produce a solid. This one here, I've got dinitrogen trioxide, and I'm adding it to distilled water. So I've got a non-metallic oxide reacting with water. A non-metallic oxide with water is going to produce an acid. And this one's tricky. Okay, we want an acid that has some kind of polyatomic ion with nitrogen in it. Okay, so your choices are nitrate and nitrite. Okay, if you use nitrate, it doesn't balance as nicely, but if you use nitrite, you can balance it nicely with 2 in front of the acid. Okay, you've got 4 oxygens, 2 nitrogens, and 2 hydrogens. Okay, so in terms of balancing, those ones aren't easy, but in terms of predicting that an acid is going to be produced, that's something that you need to know, a non-metallic oxide plus water. Okay, this one here, excess chlorine gas is passed over hot iron filings, so we've got Fe. Okay. Iron has the more common oxidation state of 3, so this is going to be the product, FeCl3. Okay. If you chose FeCl2, okay, it would be a minor error versus a major error. Okay. And then to balance this, you're going to put a 3 here, a 2 here, and a 2 here. Okay. Again, with these ones, with no indication of a solution being present, we keep them in their formulas. Okay. This one here, actually, just to mention back why I left this one as a molecule, this is a weak acid, so I keep it together even though the water is there. Okay. And this is a gas, okay, or a solid, maybe, as indicated. Okay, but there's no indication that it's something that ionizes. Combustion, so ethanol. Okay, this is, as I've said before, there's touches of organic chemistry in the AP exam, and this is an example here. Okay, I would draw out the structure, okay, to get the formula. It's C2H6O, okay, plus oxygen, burned in oxygen gas, so that means it's combustion, so you're going to produce carbon dioxide and water. And when you balance this, you get a 2 and a 3 in front. Single displacement reactions. Okay, here we've got a bar of zinc metal. Okay, so when it's just a bar of metal, there's no charge on it. And we're putting it in a solution of copper 2 sulfate. So you could do this in 2 steps to get rid of the spectator, or you could recognize that it's going to be a metal displacing a metal, so the sulfate's a spectator. So really what happens here is the copper ion becomes the metal, and the metal becomes an ion. Okay, and zinc is always 2+, and that's how I know that. A piece of sodium metal is placed in distilled water. Okay, you can use the activity series and see that, in fact, sodium does react with water, but also be confident any reactions that you're given will occur. So if you've got the sodium metal reacting with water, you know that it's going to displace hydrogen gas. So as I said before, you want to imagine this as H and OH. So the hydrogen gas gets displaced and the hydroxide remaining reacts with the sodium. Now in this case here, sodium hydroxide is a strong base. Okay, so you're going to split this up. Okay, so I should just move this over a little bit. So I should have sodium plus hydroxide minus. Okay. And in terms of balancing, okay, I need 2 here, 2 here, and 2 here. Okay, so I'm also going to need a 2 there. Okay, this one, a piece of aluminum is added to a solution of silver nitrate, so it's a metal displacing a metal. Okay, so I'm going to get the pure metal and then the aluminum 3+. We'll go over this in greater detail later on, but this actually needs to be balanced. If you did the full ionic reaction first, you would see that we need 3 in front of the Ag. Really what I'm doing here is balancing the charges. Okay, this is 3+, so this needs to be 3+. This next one, chlorine plus sodium bromide. So this time I've got a nonmetal displacing a nonmetal. So I'm going to make sodium chloride. Okay, and the sodium is a spectator. and I'm going to make bromine gas. Okay, so I'm going to get 2Cl and 2Br minus. Next one, a strip of zinc is added to hydrobromic acid. Hydrobromic acid is a strong acid, so I'm adding H plus here. Okay, the metal reacting with acid, I'm going to get Zn2 plus, and I'm going to get hydrogen gas being produced. Okay, because the hydrogen is being displaced. This complexation reaction, okay, I've got a solution of silver nitrate and excess sodium cyanide. So I'm going to produce a complex, okay, with 2, because that's double the charge, and the charge on the entire complex is going to be negative. Okay, we'll need to continue in a second video the double displacement examples.